Hi, Adam. Thanks for joining us today talking about the difference between solid state microwave versus traditional technology of magnetron. Can you share some of the key efficiency differences between solid state microwave generators and those traditional magnetron systems?
Hi, Laurie. I'd be happy to. Well, there's a number of things, but one key piece that we always look at is the solid state generators can be consistent performance throughout their lifespan. Magnetron systems generally degrade over time before they fail. You contrast that with a solid state generator; they will stay have the same power, the same output throughout their lifespan, and their lifespans are much longer than magnetrons. They have much less maintenance requirements over their lifespan, and are easier to fine tune to the performance needs and to the process needs than magnetrons. This can turn into better total cost of ownership over time because you're getting more power into your product, which is what you're trying to process.
So overall, a lot of opportunities for improvement for anybody that's in the industrial application space. I'm wondering, can we dig a little bit deeper into some of the specifics, the technical specifics? So how does load matching impact system efficiency in solid state versus magnetron?
Well, this is one of the really interesting parts of solid state versus magnetron, and I have a slide I can show you that really demonstrates the power of solid state and its frequency agility to be able to load match to what the characteristics of your systems are. And this can be seen most readily in this graph as you see on the screen. The In this particular sweep, we call it, that the software did on the particular application we're working with today, right at this very high peak, you see a very good match for the particular application. And this at 909 megahertz, you can't get a 909 megahertz magnetron. So if you want to maximize the power into your load or your material, you need to be able to shift the frequency to 909 and then operate there. Then most of your energy will be absorbed in the material. Whereas if you're running at 915 or some other frequency where magnetrons only work at, you'll have much less absorption in the material, and that equates to lost efficiency or degraded performance.
Hmm. So can you explain the significance of the frequency agility in solid state microwave technology and how it improves the processes for adaptability?
Well, one example of that would be that we've recently done a project where we simulated and characterized the material, and we found that over the cycle of the system, as the customer is heating this particular material, the characteristics of the material changes, and so there's actually a different frequency that's best used when the material gets hot versus when it first started the process. And so over time, say at the halfway point, we shift the frequency to a different point on the generator's operating band. The process can continue to be highly efficient and absorb most of the energy. This is something that you cannot do with a magnetron. Shift frequencies during the process and to maintain high efficiency. You would just lose this power, and it'd be another wasteful energy situation if you couldn't move the frequency during the middle of your processing run.
Thank you. So how does the elimination of transmission lines in solid state systems reduce energy losses?
Well, this is an interesting, and we've yet to seen really too many customers truly adopt this opportunity, but many situations come in where magnetrons are a single source of power, and to make the power, distribute the power into the particular applicator, if it's a oven for doing food cooking or drying or other applications, they split the power up and you have a big, huge waveguide distribution network. And all that waveguide, it's very efficient at at transferring the energy from the generator to the oven or the applicator, you still have losses in these systems. The really unique thing with solid state is if you have a known amount of power you need to put at your applicator, and you have many points of where many installations in industrial cases have many inputs because they want to distribute the power evenly down a long oven, for example. What you can do to minimize the need for all this waveguide and the losses associated with it is to right size the generator for that specific power need at that input port. And so we've seen, and I've worked with some projects to put just the right size amount of power there, and then you minimize the waveguide and the other parts that would have losses associated with you. And you, at the end of the day, you can squeeze out a bit more efficiency in the process by right sizing the generators at for each of your input needs.
So awesome. So as we're comparing magnetron systems and solid state systems, what role does pulse mode play in improving the efficiency of the solid state system?
Well, the pulse mode can have many different modulation schemes, but one of the features that we've implemented in our software is strictly a on-off pulse mode, and these can be enhanced in future releases of our software. But currently, ours is a on-off pulse system, which really you can think of it as terms of duty cycle being on and off. And some applications, especially plasmas, we're working with customers that are trying to leverage and improve their processes by taking advantage of that pulse feature to maintain the plasma at a lower duty cycle, and maintain the same output in their product. What that can do is if you only on 75% of the time, you will use less energy. And so the trick in the process developers in front of the process developer, what they can take advantage of here is you might be able to use less power to accomplish the same end goal, and at the end of the day, that helps improve the efficiency of the overall system. So when I think about efficiency, I think about how much power from their AC plant line to how much energy is required to process or produce the goods that you're looking to do with microwave energy. And so pulse power can really have it's not a one size fits all type of technology or feature, because some applications you can't leverage and use a pulse power for, it won't help your process improve it. But some applications it may be. And one of the things that has really not been on the market until solid state has come out is the ability for developers to experiment with this technology and this feature to see if it does benefit them, and if they can leverage it, then they can save money by being more efficient.
Awesome. Solid state systems offer higher precision in controlling microwave output. How does this precision translate into benefits for specific industrial applications such as plasma processing or heating?
Well, we've been doing a lot of documentation and trials internally to quantify just that kind of question, and we've seen that we have very precise power control on our output, and we can have this data available for anybody that would like to see it. But the level of power that we can output can be maintained, 24/7 for many, many days, or however long they need to run the process. And that's not the case with Magnetron, where you're going to have a slow degradation over time, and you'll have to make other adjustments to keep the process running, especially if you're running a 24/7 application, for example, in diamond growing or other continuous processes that in plasma applications or pyrolysis processes. The precise power piece of it also can be used in conjunction with a temperature control system, where you can monitor the temperature of your product. And if you need to control, you have a threshold where you say I cannot be higher than a certain temperature. The solid state generators are very fast acting and can be tuned to minimize that, eliminate that overheating that you might see with a magnetron. Because magnetron systems really can't turn the power down very fast. You can turn the power down or turn the power up on a solid state generator within a fraction of a second. It takes 3 to 5 seconds at a minimum to turn the power up and down on a magnetron system, and you may find that you have over either under application, undercooking, or overcooking using a magnetron when you don't have that ability to really precisely control how much power you apply. That problem is eliminated with solid state.
Awesome. Thank you. And what future trends in solid state microwave technology do you foresee that will further improve system efficiency and reduce costs?
We're seeing a number of things, as I mentioned before. That the transistor manufacturers are continuing to improve their products. They're continuing to improve the power output of their devices. They're doing both at the same time, in fact. And while certainly a 10, 15, 20% improvement in their efficiency will translate to higher efficiencies in our end systems, they're also having higher output power. What that will do is lower the number of components that we need to aggregate and design and build to make a comparable generator, say a 50 kilowatt generator. If we have transistors that are twice as powerful as what we currently use today, we'll have half as many circuit boards and other devices that need to run those transistors. So that will definitely drive a lower cost of ownership, a lower CapEx cost to buy the generator, because we'll be using less components and it'll be easier to assemble. And so these two things are certainly in the mix. There's other types of approaches that we're looking at to enhance the efficiency of generators, as well as these basic transistor improvements that are coming online as well.
Awesome. And from an operating cost and OpEx perspective, what are some of those life cycle cost differences between magnetrons and Krishan's solid state microwave systems?
Well, the biggest one is you don't have magnetron tubes to replace. And really it's there's a huge range of applications that are out there in the market with using magnetrons, obviously, but there's certainly some newer technologies that are coming online. I mentioned diamond growing, for example. While the magnetron folks may say that you can get 6 to 8 thousand hours out of these devices, many times customers, because of the degradation problem I mentioned before, they have to change these out much less time, maybe 3,000 hours. And so the life cycle cost is definitely impacted, because if you have to replace these tubes every 2 to 3 months, that's a continuous cost to the operation to keep product moving. This problem doesn't exist with solid state, where we design our systems for 10 to 20 year lifespan, and these have really very little maintenance other than some filters, air filters for their cooling systems. But these are very inexpensive pieces to replace when's needed. So this really should be a point of emphasis to look at when you have a certain process that, for example, 24/7 processes, which are being more and more of these are being developed around microwave energy, and the cost of a failure, because sometimes tubes can fail unexpectedly, and if there's a significant cost to restarting the process, those impacts need to be thought about when choosing your microwave generator. If that's a significant cost that can be minimized or eliminated with solid state, those total costs, those costs should be factored into the equation when you're evaluating what type of technology to adopt.
Awesome. So virtually no downtime could really improve the throughput and the operational efficiencies of a plant being able to operate 24/7 with that, again, virtually no downtime since we're not replacing magnetron tubes.
Right.
And anything else that I didn't ask that came up in your mind about the differences between solid state generators and magnetron systems?
Yeah, I think that we're seeing a tremendous interest in we're working with new technology companies that are using our generators to start with. They've found them to be very, very helpful. This is really you can speak to I can speak to our precise power software where it's been an analytical tool that really enables the customer to see what their system is doing and what the impacts are with changes that they make in their system. And from that information feedback that they get, they can quickly make changes to their process to get that product and that process online and running. This was a little bit of a dark art before when you were kind of running blind and you couldn't see this real-time information. Solid state changes that, and you have now there's a little bit of an opening of the window and letting in the fresh air where you can see things that are happening and move that process along faster. So we're seeing really good feedback from uh, technology developers from the lab up to larger scale. They can really see some good benefits using the software that we produce at Crescend.
Awesome, Adam. Thank you so much for your time today and your expertise. Appreciate all of the answers to the questions. Thank you.
All right, have a good day.